Hello, calculus students. These are notes for section, let's see, where are we? 7.6. How to find the average value of a function. And also, I'm going to talk about how to use this and some other general ideas in context. So we'll say and applications. But let me just stress that it's not just application of this, it's applications of the general ideas, I guess maybe moving away from just our velocity, acceleration, and position type problems into more general contexts where we have rates. All right, so anyway, first of all, how do you find the average value of a function? Well, let's look at a function, f of x, and say, I want to know what the average of that function is from here to here. Well, normally when we find averages of things, for example, what's the average of the 7172 quiz grades, for example? Well, there's 24 of you in calculus this year, so I would add all those up and divide by 24. So let's see if we could do that here. The values of the function, so I could add up all the values of the function and then divide by how many there are, but that doesn't work because that's infinity over infinity, right? That's not going to work. Before you get all excited about infinity over infinity and thinking about L'Hopital's rule or something, we can do something a little bit easier than that. We're going to say here that there's an average value of this function. Maybe it's somewhere about here, I don't know, here, somewhere in this area, right? Would be the average. But how do we define that? Well, we're going to define it to be, you could imagine a rectangle, this rectangle right here. We're going to define the average value of the function to be the height of the rectangle that has the same area as the area under the curve. So let's look carefully at the picture, make sure you understand that. So here's the area under my curve, right? All through here. And somewhere there's a rectangle. There's some height that when we draw across there, it will have exactly the same area. So we call that height, we define that to be the average value of the function. It's the area of the rectangle, or the height of the rectangle, I should say, that has the same area as the actual area. Now that gives us an equation, right? What is the area of that rectangle? Well, the area of that rectangle is the height of the rectangle, which is that average value, times the width of the rectangle, which would be b minus a. And we want that rectangle to have the same area as the actual area. Of course, we represent that like that. And then, solving for average value, we just get the average value is equal to the integral, or the actual area, divided by b minus a, divided by how wide the interval is. That's how you find the average value of a function. Now, maybe you're thinking to yourself, well, this is confusing because I run into the word average sometimes, and when I see the word average, I get confused and I'm not sure exactly what I should be doing. Well, this actually should help clarify what you should be doing. So, for example, find the average velocity on the interval t equals, let's say, 1 to 3, if our position function is equal to t squared plus 9. Well, there's two ways to do this problem now, right? There are two different ways we could do this. First of all, if you actually understand what average velocity is equal to displacement divided by time. So average velocity is equal to change in position over change in time. change in position, that's x3 minus x, x of 1 over 3 minus 1. And that's, let's see, 18 minus 10 over 3 minus 1, which is 8 divided by 2. So the average velocity is 4, right? Now that's the definition of average velocity. But if you were thinking about this, well, what about the average value of velocity? Can we do it that way? Well, sure. You could say, let's see, here's my position function, but if that's the position function, then velocity is just the derivative of that. That'd be what, 2t? Right? And then, if we go back to here, we could say average value of the velocity function is equal to the integral from 1 to 3 under the velocity curve, right? I'm finding the average of velocity, right? So I would actually put velocity here, divided by 3 minus 1. And let's see, antiderivative of that is t squared. So t squared from 1 to 3 divided by 2, and t squared, that's 9 minus 1 over 2, which is equal to 4. So we get exactly the same thing. So you need to, when you see average whatever, you've got a choice here. And it really, what direction you go should depend on what you're given, right? If you want to find the average value of velocity in your given position, probably this is the way to go, right? But if you were trying to find average value of velocity and you are given the velocity function, then this is the way to go. But notice that they give us the exact same answer. So it's not like you have to remember two different average things to do. Either one will work. Okay? Now, you can try some examples of how to do that, but it's a pretty easy thing to do. Let's take a look at some College Board problems, but let me just make a general point here. In general, if we take the integral of a rate, which I'm just going to call r of t, rate, and maybe I'll call it r prime of t, right? It's the rate of change of something. Of what? I don't know. Maybe a population, maybe the amount of rainfall that's accumulated. I think in the next example we're going to look at, maybe it's the amount of the number of people that have entered an amusement park. That's another problem that you'll see. But it's a rate. It's measuring the rate that something's changing at. In general, if you take the integral of this, it gives us a kind of displacement, right? If we do this with velocity, we know we get displacement. But this isn't velocity, it's just some general rate. Well, what does it give us when we do that? It really is like a version of displacement. We know by the fundamental theorem to evaluate this, we find the antiderivative, which would just be the r function. So what does it mean when we find this, this integral? It means that we find the amount of change in whatever the original function is. So that's just a general idea, and we're going to put that into practice here with a couple different problems. So if that still seems a little fuzzy to you, how you would do that, then check this out. These are a couple problems, I think, from the 2011 administration of the A/B test. So a cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. The can's initially empty, okay, so it's starting empty, and rain enters the can during a 60-day period. The height of the water in the can is modeled by the function s, where s of t is measured in millimeters and t is measured in days. The rate at which the height of the water is rising is given by this s prime, right? So this is a rate. This is the rate that the water is changing at. Okay, now, according to the model, what is the height of the water in the can at the end of the 60-day period? Well, how am I going to actually find the height at the 60? I mean, that's like an S value, right? I want to know, as this is S of 60, right? But I don't have the S function. I only have S prime. Well, to get from S prime back to S, that's where we set up this integral. So we're going to do the integral of the S. That's going to get me back to S. But it's not just, this isn't equal to one particular value. We have to go from, typically we're going to go from the value we know to the value we're interested in. Why did I choose 0 here? Is it because we always start at 0? No. Often we do, but I picked 0 because I know that S of 0 is equal to 0. Right? Right here it says the can is initially empty. That means S of 0 is 0. That's why I chose 0 here. So this is equal to S of 60 minus S of 0. This should feel a lot like a velocity displacement kind of problem here. So I know this. This is 0, and I can put this in my calculator. So let me go ahead and do that. My old-fashioned calculator, so sorry for you math print folks. I'm going to go math 9, that's fn int. My function is 2 sine of 0.03 x. Oops, I opened another set of parentheses there, didn't I? Didn't need to do that. Close that. Plus 1.5 comma x comma 0 comma 60. That's evaluating that integral. And I'm just going to make sure, yeah, I thought from physics I might be in degree mode, so find that. 171.813. So that's 171.813. That's this is equal to S of 60 minus, and oh, oops, off my page there, minus 0. Right? Sometimes there's a number here. Oftentimes, I would say most of the time, there's a number here. In this case, we actually got S of 60 is equal to 171.813. And what are we talking about here? Let's think about what the units are here. This is an S, a height minus a height. So this is a height in millimeters. Right? Many of the points in these types of problems are assigned to having an understanding the correct kind of units. Right? So looking at this, this is a height minus a height. That's going to be in millimeters. Those are the units of the problem. Part B, according to the model, what's the average rate of change? Hey, the rate of change is the S prime. So I want to find the average value of S prime over the 60-day period. Okay, so to find the average, I do the integral from 0 to 60, S prime of t dt. And by the way, I just found that number. There it is. Divided by the b minus a, right? So that's 171.813 divided by 60. That gives me 2.864. Now let's think about the units for this. It says indicate units of measure. You want to leave them off? Hey, that's fine, but you're going to lose points for that. So let's try to get the units right. This is the rate of change of the height. So that means it's in units of height per units of time. And that's, I believe that's days, right? Yeah. So that's millimeters per day. 2.864 millimeters per day. The average, the units of the average of something are the same as the units of the thing, right? If you have a bunch of test grades and they're all worth so many points, when you find the average, it's in the same units, points. So got to use our average value thing there. That's cool. Part C says, assuming no evaporation occurs, at what rate is the volume of water in the can changing at time t equals 7? Indicate units of measure. So no evaporation is occurring. At what rate is the volume of water in the can changing? That's just S prime of 7, right? This is our rate that the water is changing at, right? So I just need to plug in 7. Sounds harder than it is, but the at what rate is the volume? Just kidding. Volume of water, right? Okay, let's try that again. So volume, in this case, since it's a cylindrical can of radius 10 millimeters, volume is equal to pi r squared h. So volume is equal to pi times the radius is 10 squared times h, right? And if I take the derivative of this, let's see, that would give me dv dt is equal to, that's 100 pi, that's just a number, times the derivative of h, dh dt. But the rate that the height is changing at, this is s prime, right? That's what that function is. Remember, the rate at which the height of the water is rising, that is s prime. So I think what we want to do is we need to do 100 pi times s of 7. So let's see, that's 100 pi times s of 7, which is 2 sine of 0.03 times 7 plus 1.5. And check, see if that looks like I've entered that all right. I think that that's correct. That gives me an answer of 602.218. I'm going to ask you to pause for a second and think about what the units would be for this. All right, the units here, volume is in cubic units, and our units here are cubic millimeters. Time is measured in days. So it would make sense that the rate of change of volume would be measured in cubic units per time unit. All right, so that was a little bit of related rates they snuck in there. And last part. During the same 60-day period, rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. Height of the water in the can is modeled by the function m. So this is the actual height, m, right? Notice that this is not the derivative. It's measured in millimeters, and t is measured in days. Now let d of t equal the derivative of this one minus the derivative of the other. Apply the intermediate value theorem to the function d on the interval 0 to 60 to justify that there exists a time, 0 to 60, at which the heights of the water in the two cans are changing at the same rate. Well, we want to try to find a time, or show that there's a time. We don't actually have to find the time when that these two are changing at the same rate. So, well, same rate means the same rate. That would mean that the rates of the two cans are equal, right? And that happens when the d function, if those are equal to each other, that's going to make the d function equal to 0. So what we need to find is, remember what the intermediate value theorem says? It says if you've got, in this case, since we want it to be equal to 0, if we can find a negative and a positive, since this is a continuous function, we just need to show that it would have to cross this, right? If we can find a negative value and a positive value for the d function. So I'm going to try d of 0. That's, well, let's see, m prime of t, so that's 1 over 400 times, the derivative of this is 9 times 0. Sorry, let me go back up here and write down what the derivative is. I'm kind of cutting too many corners here. 1 over 400 times 9t squared minus 60t plus 330. Right, that's the derivative of the m function. So that's 9 times 0 squared minus 60 times 0 plus 330 minus s prime of 0. So let's see. 1 over 400 times 330, that's 0.825, minus 2, let me see if I can just bring this thing back up. And what do I want to plug in here? I want to plug in 0, right? Whoa. No, I didn't want the 100 pi there, did I? Just want the value of this function. There. That's too many parentheses now. That was probably more trouble than it was worth. Okay, so that's what I want, right? I want to plug 0 into that. And that's 1.5. Probably could have figured that out without a calculator. And that is negative, right? And then d of, let's try 60. Let's just try the endpoint and see if we get a positive. Now, plugging 60 into this, I get 1 over 400 times 9 times 60 squared minus 60 times 60 plus 330. That's 72.825 minus the, let's bring that back up, minus this, but I just want to make that 60 now, right? That's 3.448. But anyway, certainly a positive number, right? So I went from negative to positive. So this is the last line to get all the points here. We need to say, since dt is continuous on the interval from 0 to 60, and d of 0 is negative, while d of 60 is positive, the intermediate value theorem says that dt must be 0, right? Any number. In fact, it could be any number in between these, right? In between whatever that is and whatever that is, right? But 0 is between those, negative and positive. So it must be equal to 0 at least once in the interval t from 0 to 60. Right? Intermediate value theorem is pretty easy. Just says it's got to cross every number in between this and this. And all we were looking for was a negative and a positive. And should you come across something like that, certainly the endpoints are a good way to start. So that's kind of the idea here. Really the biggest ideas in this problem relative to what the new stuff is that we're talking about now are parts A and B, where we're using this idea, the fundamental theorem, applied to some rate besides velocity and average value. So that's why I picked this problem. It had both of those elements in it. Alrighty, onward to try some problems.